done. So without further ado, we'll have our first speaker come up. Introduce you. All right, our first speaker this morning is Maria Gonzalez, who's joined us from Caltech. Maria's been working this summer with David, and today she'll tell us about their project together, modeling core collapse supernova beyond shock breakout.
All right, thank you, Gwen, for the introduction. Good morning, everyone. Thank you for coming. I'm very excited to start off the CASI Symposium with my research. Core collapse supernovae are the explosive deaths of massive stars typically greater than 8 solar masses. These core collapse supernovae are extremely influential to the evolution of our galaxy as they produce and distribute numerous elements including iron and oxygen. They also leave behind compact remnants like neutron stars and black holes. As such, we want to understand as much as possible about the explosion mechanism behind core collapse supernovae. Currently, our understanding is that as a massive star undergoes nuclear fusion, it reaches a point where its innermost core consists of iron. At this stage, the core can no longer support its own weight against gravity and undergoes core collapse. During this process, neutrinos are produced, which are essential for transferring energy from gravity into explosion. What exactly do these explosions look like? We see an example in the Crab Nebula, which is a remnant of one of the oldest recorded supernovae. This Crab Nebula has an extremely asymmetric structure. Inside, we see an inconsistent web-like feature, and also on the overall shape is not very spherically symmetric. This is because core collapse supernovae are asymmetric at all scales. And the Crab Nebula is not the only example. We see similar features in Cassiopeia A, which is one of the best studied remnants of a supernovae in our galaxy. In Cass A's nickel, silicon, and titanium-rich ejecta has a very asymmetric structure. We see jets that are shooting out of the remnant, and the colors here highlight the asymmetries in the ejecta morphology. For instance, we see this dark blue pocket within the remnant itself. And like the Crab Nebula, Cass A highlights the inherently asymmetric nature of supernovae. Understanding the origin of these asymmetries becomes increasingly essential as new instruments like the James Webb Space Telescope provide us with numerous detailed observations of core collapse supernovae. In the previous slide, I showed an image of Cass A that was taken by the Chandra telescope. Since then, the James Webb Space Telescope has provided us with newly resolved images of the same remnant. And this is not specific or exclusive to Cass A, as new instruments provide us with tens of thousands of new observations of core collapse supernovae every year. We can use this new abundance of data to then build strong theoretical models of the explosion. However, one of the biggest constraints of these models is how asymmetric the explosion is at all scales. The explosion from core collapse supernovae produces a shock that emerges from the core and propagates outward, sweeping a material as it does so. One might expect this shock to be spherically symmetric, as shown here. However, simulations show us that asymmetries are actually seated in the shock within seconds of the explosion. Thus, the shock is actually extremely aspherical. I also wanted to take this moment to clarify some terminology specific to my research. I'm studying core collapse supernovae beyond shock breakout, that is, when the shock emerges from the stellar envelope into the circumstellar material, or the material around the star. This event is closely associated with first light. And not only do these asymmetries exist, but they also persist throughout time. Previous research utilizes three-dimensional hydrodynamic simulations that allow us to analyze the evolution of these asymmetries on a scale of hours to weeks. Here I'm showing you a low-energy 9 solar mass model, specifically an equatorial slice plot of entropy. We specifically chose entropy because it creates a strong contrast that allows us to see features of the shock, such as the forward and reverse shocks. Here we see interior to the shock this mushroom-like structure. And on a grander scale, we see that in the northeast hemisphere, the shock is traveling at a greater velocity compared to the majority of it traveling at a slower pace. Again, this is because these asymmetries are very prevalent in the supernovae at all scales. And we not only see this in the shock, but also in the ejecta morphology. This model of the nickel distribution of a core collapse supernovae shows asymmetric features appearing at 5 seconds after explosion, seen on the left. Here we see that the overall structure is dipolar, and there are also these mushroom-like features that are already appearing. On the right, at about 6,000 seconds after explosion, we see that the overall shape remains the same, and we again still see these cloud-like features. This is despite looking at a timestamp more than 1,000 times later. However, this model only shows the evolution of the shock as it propagates throughout the star. But what happens next? Currently, there are an insufficient amount of three-dimensional detailed hydrodynamic simulations showing the shock's evolution into the circumstellar material. And we do see evidence in Supernova 2023 IXF of the circumstellar material interacting with the shock in its observed light. All of this leads to my research question, which is answering how the circumstellar material influences the shock dynamics of core collapse supernovae. To answer this question, I developed three-dimensional hydrodynamic simulations using the code FLASH, and I followed the supernovae from shock breakout into the circumstellar material. This is an image of my initial condition, which is a 17 solar mass progenitor. We specifically chose this explosion as it is high in energy and has an abundance of nickel. My mentor takes this explosion and develops it up to shock breakout, which takes 1 day to reach. And this is where my research begins. I take this explosion and then I surround it by different models of the circumstellar material, where I then run the code through Flash. My first step is to actually create these different profiles of the circumstellar material. This entails changing the density to either have a constant, power law 1 over r squared, or a hybrid density profile. We specifically chose the constant and power law profiles as they have been historically used. And the constant assumes a uniform density environment with radius, whereas the power law assumes a uniform mass loss rate. The hybrid combines a power law and exponential equation to better model circumstellar materials that are heavier on the inside and less dense on the outside. I also vary the mass of my models to either be 100th, 1/10, or 1 solar mass. Here, I plotted all of the initial profiles of the circumstellar material, specifically the mass and the density. For the sake of this presentation, I'm going to be focusing on my power law models with the varying masses. This is because an interesting finding that we had is that the circumstellar material mass was the main driver for any changes that we saw in the asymmetries. After I develop these profiles and stitch it onto my initial condition, I then run my simulations using high-performance computers at the Texas Advanced Computing Center. This has led to over a dozen successful simulations ranging on a scale of hours to weeks in the shock's evolution, and this is excluding the 1 day that it took for my initial condition to reach shock breakout. After I run a simulation, I'm then left with output that allows me to illustrate the evolution of various properties as the shock propagates throughout the circumstellar material. Such properties include the kinetic and internal energies shown here. For all of these low-density circumstellar material models, we expect the kinetic energy to increase and the internal energy to consequently decrease. An interesting finding that we had is that the difference between the minimum and maximum kinetic energies is about 15%. While this is significant, considering that we varied the mass the mass of the circumstellar material by a factor of 100, this was not as pronounced of a difference as we initially expected. And we see a similar pattern when looking at my power law models with 100th, 1/10, and 1 solar mass. In playing these movies, what we see is that for the lowest solar mass model, or circumstellar material mass model, the shock velocity is more than twice as high compared to more massive CSM. Furthermore, we also see that for the same model, the shock sort of balloons outward, whereas for these more massive circumstellar materials, we see these sort of dimpling effects that appear as the shock encounters more resistance from a heavier environment. A final observation that we made here is that as you decrease the circumstellar material's mass, the shock itself also becomes more off-axis. We again see similar patterns when looking at the ejectomorphology. Here, for the same models, I am looking at the nickel distribution, and what we see is that as we increase the circumstellar material's mass, the ejecta becomes more confined. Furthermore, we sort of see these noses that are appearing in the lowest mass model that, again, are not as pronounced as you increase the circumstellar material's mass. We also wanted to explore how much of each isotope mass is mixed beyond the stellar envelope. We see here that the nickel ejecta, shown in blue, decelerates and surprisingly mixes back in as it encounters a heavier environment. We can also see this when looking at the kinematic evolution of the ejecta through this movie depicting isotope mass and the velocity distribution. I recommend that you focus when I play this movie on the yellow, which is the nickel, specifically because nickel is formed in the core during explosion and it mixes outward with higher energy. If I'm playing this movie, we see that the nickel initially accelerates and then decelerates as it encounters a denser environment. And again, some of it is mixed back in as I previously showed. Thus, through the late time simulations of over a dozen models into the circumstellar material, we observe structural differences in both the shock velocity and the ejecta morphology as the shock propagates through the circumstellar material. We also saw the similar patterns in looking in the mixing fractions and the ejecta velocities. In the future, we want to run even more models with different explosions and greater masses, and we also want to evolve them into later times. And an overarching goal is also to synthesize light curves with the goal of directly connecting our simulations to observations. And all this is with the final objective of seeing how this circumstellar material's interaction with the shock influences asymmetries that are prevalent among all supernovae. Thank you.
All right, questions for Maria?
So you make the assumption that the circumstellar material is homogeneous, or?
Yes, we do. And then we just stitch it onto the initial condition. Yeah, that's a good question. All of the profiles that we use are physically motivated. The only one that has a constraint in terms of the circumstellar material's mass is the hybrid profile that is not physically motivated once you reach circumstellar material masses above 3 solar masses. Yes, thank you.
Great, let's thank Maria again.